9.6, today we're going to be taking a look at our last two tests for convergence. These are the ratio test and the root test. And there are some similarities between them where it makes it sometimes difficult to decide which one for sure is the better choice on a particular series, but there's also some differences that help us out too. So as we take a look, we'll start with the ratio test. So we have a series, n equal 1 to infinity, and they're non-zero terms. Then this series will converge absolutely when the limit of the absolute value of the ratio of successive terms, so a sub n plus 1 over a sub n, is less than 1. If that limit is greater than 1, it diverges absolutely. That's what I want. And if it actually equals 1, it's inconclusive, which means you can't use this test, right? Strike out. Yeah.
If it were to happen to equal 1, could you possibly use another test?
Yes, exactly. Then that's what it would mean. It would mean that this is just not a test that will work for that particular sequence or series.
So this test will work for everything that is not equal?
Well, it will be helpful and usable sometimes and not helpful and not usable at other times. Okay? So it's not like the go-to, I can always use this. It doesn't work like that. Sometimes you can figure out that limit value easily, and sometimes you can't. And when you can't figure out that limit value easily, it's just probably not a good test to use. So the third line on here is simply telling you when it absolutely is completely useless, right? It's useless if you're in case number 3, but it doesn't necessarily mean that you're always going to be able to find the ratio and it to be less than 1 or greater than 1 in an easy fashion. Does that make sense?
Yeah.
Okay, notice it does also say non-zero terms. It doesn't say they're positive or they're increasing or decreasing. It just says they're not zero. So we may have positive or we may have negative or we may have some of both. That's okay. Notice that the limits that we're taking are in absolute values, so the positive or negativeness of it is irrelevant at that point. It's all positive. Okay, I think we're good on description. You ready for some examples? Okay, ready when we are, okay. Okay, here's our first one. So one of the things that you'll often see when the ratio test is useful is factorials. So you can write that down as a note to yourself. When I see factorials, this might be a good test to use, okay? So that's what's going on here. I don't have zero terms here, agreed? Yeah, these are non-zero terms, so that part's good. Typically speaking, that's not a problem. Most of our sequences do not have series with zero terms. That's not something that happens frequently anyway. And it does have that -1 to the n at the beginning, so it's going to oscillate, like alternating series kind of stuff, which also may mean that you could use alternating series on this, right? Like that might be an option. We're just not going to use it for this particular one. I'm going to show you how to use the ratio test for this. So we're going to take the limit as n goes to infinity of the absolute value. And you know what? I'm going to leave the -1 to the n off. You guys good with that? Because we know it's going to disappear at the absolute values anyway. Okay. So it says the n plus 1th term. So that's 6 over n plus 1 factorial. And then it's divided by the nth term, which would be 6 over n factorial. And complex fractions are not necessary. We can rewrite that. Oops. By using the reciprocal. So this is 6 over n plus 1 factorial times n factorial over 6. Is that all right? Okay, so what's going to cancel? Okay, 6's are going to cancel. That's true.
The n plus 1 factorial and the factorial on the n.
Okay, so n plus 1 factorial would mean n plus 1 times n and all the way down to, I'll keep going, all the way down to 1, right? Like that's what it would mean. And if I did n factorial on the top there, I'd have n all the way down to 1, right? Okay, so you're really close on how you said it, but you said it sort of flipped.
Yeah.
Yeah, no problem. Okay, so as we're looking at what's going to cancel here, then we have the n factorial that cancels, and the n plus 1 remains. So I'm left with the limit as n goes to infinity of 1 over n plus 1. Is that okay? So what is that limit? Yeah, this one happens to be 0. And we didn't really need it to be 0. We just needed it to be less than 1. But 0 will work. Happy with that? So this is less than 1. So what does that mean?
Converges absolutely.
Uh-huh. It converges absolutely by
Ratio test.
the ratio test. Yep. And can you see why it's really nice to use the ratio test for things with factorials? Yeah. They often work really nice. Yeah. Uh-huh.
How would you go about the alternate series test? If there was one with factorial?
Yeah, so if you were looking at the alternating series test, we would eliminate the negative one part, and we'd still be looking for if that sequence, what was inside of there, the sequence itself went to 0, and it would, because you've got something that's infinitely large on bottom. So the sequence would still go to 0. It would still work. Justifying it with some sort of algebra technique might be a little bit more difficult. Writing out an explanation might be usable, though. Yeah.
So if we had done would it have been better if we did the ratio test for that factorial?
For factorials, it's more natural. It's a lot easier to prove with algebra simply than it is to work with like a justifiable explanation in words. Yeah. Okay, so factorials. Another thing that you will often see for the ratio test where it's useful is when you have powers of n. Okay, so let's take a look at this one. I have a series, n equal 1 to infinity, of n times 6 over 5n. And as long as n's bigger than 1, right, n is 1 to infinity, this is non-zero, correct? Yeah, so we're good to go. So we're going to take the limit as n goes to infinity of the absolute value. And you know what, again, I'll put it in absolute values this one time, but these terms are all positive, yeah? So the absolute values are a little bit of an overkill statement here. They don't actually even eliminate like the negative 1 to the n like the last one did. But I have n plus 1, and then I have 6 over 5 to the n plus 1 over n and 6 over 5 to the n. Okay, so far so good? Okay, so what could we reduce here?
Exponents, shouldn't they end up canceling out a little bit?
They do cancel out a little bit. One way to do that is to remember properties of exponents, which may be where you're thinking, Caleb. I can actually subtract n plus 1 minus n, right? Properties of exponents. So this is just going to be 6 to the 5th, or 6/5. What was that?
Then can you cancel them out?
Not quite, because one's going to have a 6/5, and there's not going to be anything in the other one.
Oh, okay.
So if I used properties of exponents, let me just write it down as one option. You'd have 6/5, and it would just be n plus 1 minus n, and you just get 6/5.
Yep.
So that's what would happen if you use properties of exponents. If you think about like what n plus 1 means, what it actually means up here is that I have 6/5 to the n and 6/5 to the 1. And you can see the 6/5 to the n clearly canceling if you think about it from that perspective too, right? So this is a properties of exponents sort of argument. I will do it the way that you guys saw it. So the limit as n goes to infinity of n plus 1 over n times 6/5 to the 1. So thinking about it from this perspective of subtracting the exponents is what we did. All right, so now what?
Can we move the 6/5 out into front of the limit?
You could if you'd like. It's not going to be affecting anything, so it is a constant multiplier. We do have a property of limits that allows that. Okay, enough on the side of the screen, it's not wanting me to keep writing.
Because then we could multiply by 1 over n, and it wouldn't be
Yeah.
messy.
And it wouldn't be messy, I agree with you. So if I have that in front, and then I have n plus 1 over n, and I multiply by my 1 over n, like this, I still have my 6/5. And I would get 1 plus 1 over n over 1. What will the limit part equal? Yeah. So, whoops, sorry about that. This piece will equal 1, but the 6/5 in front means it's actually going to be 6/5 times 1, or 6/5, which tells you what? Greater than 1. Yeah, 1's our reference point. It's greater than 1. So what does it mean in the ratio test if we have this limit and it's greater than 1?
Diverges.
Diverges, absolutely, exactly. So this diverges absolutely by the ratio test. So there's 2 tests that are my favorite to use, the ratio test and the geometric series test. I like those the best. I don't know exactly why, but those to me just flow and feel very natural. The next one, the root test, can be used on problems kind of like the one we just did, but they don't always, but they also have other ones that they can be used for too. So let's take a look. All right, the root test. Some of the pieces of this look just like the ratio test. You notice at the end of every line it tells you is less than 1, it's greater than 1, is equal to 1, right? Those pieces are all the same. You notice it talks about converging absolutely, diverging absolutely, and being inconclusive. Those pieces are all the same. So the part that's different is that instead of taking the ratio of a sub n plus 1 over a sub n, we're taking the nth root of a sub n. And we're using absolute value of a sub n to be clear. You'll also notice we have an additional condition on number 2, which says that if the limit is actually equal to infinity, that this is okay. You might look at that and say, well, isn't infinity bigger than 1? And the answer is the concept of infinity is bigger than 1, but remember infinity is not a number, and that's why they write it separately. So for your limit to actually be infinite means that it doesn't have a limit. That's what that second line says at the end, and that's how they're writing it separately, or why they're writing it separately.
And wasn't that the same for the ratio test?
Oh, it was. I'm sorry, and I think I just glossed right over it. You're right. Thank you. Yeah, if it's infinite, that's why that's showing up that way. Sorry, I didn't think to say it up there. Right. So that's why those are listed separately. Okay, ready to try a couple? So on these, you will see the sequence with a power of n. Okay, so you see number 3 and you see number 4. They have an nth power in them. How is that a little different than number 2?
Is it constant inside?
Close.
Well, there's no variable being multiplied across.
Okay.
Variables in the power?
Okay, like this, the end at the beginning, is that what you're talking about? Yeah. Okay, so the fact that there's a constant inside isn't a problem. It's true, it's different because it's a constant, looks different. But the real problem is that n. If I were to take the nth root of n, that's not so straightforward. Agreed? I mean, nth root of 6/5 is fine. Of the 6/5 to the n, the n's are going to cancel. But the nth root of n is going to cause a problem. So you do not see that happen in the ones that you're going to use the root test for. However, that doesn't mean that we couldn't take this problem and do the ratio test with it, or one that would be like it. That's a possibility to try as well. Probably wouldn't here because we have quite a bit going on inside of the parentheses before we're raising it to the n, right? Like if I replace the n with the n plus 1 in there, it starts to get messy to make my comparison. So the root test is a good place to go for this one. Whoops. let's use this. So we're gonna do the limit as n goes to infinity of the nth root of 4n over 5n plus 1 to the n. I probably should just at least verbalize the fact that these are non-zero terms, right? It's supposed to be non-zero terms, which they are. And then also that I don't really need my absolute values because not only are they non-zero, but they're also positive. So that's why I didn't write the absolute value, though that's understood that it's okay in this case. All right, so of course the whole point in doing that is that we eliminated the power of n. So I end up with the limit as n goes to infinity of 4n over 5n plus 1. And then what would I do? You could use L'Hopital's, sure, we'll use that one this time. You could also multiply 1 over n like we did a moment ago. So if we do L'Hopital's, what do I get? What will I get?
4/5.
Yeah, so you get 4 and 5. So you have 4/5. So it is just 4/5 then. We could have ended up with still a variable to deal with, but we don't. So what does that mean?
It's less than 1.
Ah, so this is less than 1, and
It converges absolutely.
it converges absolutely by the root test. Okay. Number 4. Non-zero? Yes. And positive? Yeah, it doesn't have to be positive, but it means I don't have to write the absolute value, so I'm going to check it anyway. So the limit as n goes to infinity of the nth root of n over 500 to the n. Okay. So I got the power to cancel. What is the limit as n goes to infinity of n over 500? That's infinity, right? Don't get confused and think you're seeing 500 over n. It is n over 500. This is infinite, which means what?
Diverges absolutely.
It diverges absolutely by the root test. Okay, the last part of this section we're going to look at today anyway is identifying different tests that can be used for a sequence or for determining if a series converges. So there's a note here, it's about page, this says 632, and in your paper I wrote 636, so I don't know which word it is.
636 is correct. I have it right
636 is correct, so I had a typo when I transferred it over.
here. Little chart of all the
Thank you.
tests.
636, we'll go with
Very
that.
helpful.
All right, so page 636 has an excellent test summary. I mean, it's excellent. Like, if you're going to study for the test and you want to lay it all in one place, that's the place to go. It's fantastic. And you're going to want that when you come to class next week, because we're going to, on Monday, when we talk about this in class, we're going to spend a lot of time with that table. And it's all in a concise form. So we're going to take a look at 4 of them together and try to decide what test we might want to try. And we may come up with more than one option on one to try too, and they might both work, and we might find that one would be a better choice than another, okay? So we're going to take a look at 4 of them, and the first one we see here is the following. So we have the summation from k equal 1 to infinity, don't know where that infinity went, but it's supposed to be there, of k factorial, e to the k over k factorial. So, what test do you think might be good to use?
Ratio.
Why?
Factorial.
Yeah, the ratio test is fantastic here. This is the key. And to be honest, that e to the k is also helpful, right? We saw that happen in the first one that we did on number 1, actually, too, where we had a power, and power is eliminated nicely when we have the ratio test. So that's also helpful. So the ratio test would be one to try. Now, it's not asking us to actually do it. It just says name a method. That's all it says right now. We're not going to do it. We're just trying to decide on methods for the moment. Okay, how about number 6?
alternating series
Seems like a reasonable one to try. How come?
is the negative 1 to the k.
Yeah, the negative 1 to the k seems like a good place. Alternating
Alternating series.
Yeah.
alternating series seems like a good spot to go with. Remember, alternating series is actually really nice to use too when it works, because I get to find the limit of a sequence, and limits of sequences are much easier to work with. So when I work with an alternating series, I'm just looking at this piece right here and saying, well, what's the limit as that goes to infinity, right, as the k goes to infinity. So it's a nice one to work with. Yeah, it is 0. How about number 7?
Integral.
Hmm? Okay, so you might try integral.
On 7?
It does, because it's
It
to
does,
the
yeah.
negative.
Uh-huh. And P series will work too. Yes. So there's a couple options to try. And I think they'll both work. P series is what I have written down, but I think integral will work on that, and you'll be okay to use it too.
P series would be quicker.
Yeah, P series would be quicker.
Integral.
P series are lovely when they work. Yeah. Yeah, and so if some of you are looking at this going, I don't see a P series, remember you would just rewrite this like this,
With the,
right?
This was
So
the
that's the
absolute
P
value.
value.
huh?
What's that?
The absolute value. Okay, that's a.
For what?
Oh,
For
no, I
P
see.
series?
I know. I was just
Oh, no.
overthinking it.
Yeah, no, not on that one.
Very.
We've got a lot that do have absolute values involved, but not the P series. How about number 8?
Why is there 2 variables?
Oh, because I wrote it in there wrong. I think it's supposed to say n up there. Let's go with that. Is that what is on your paper?
N squared.
Yeah,
It's actually
Somebody tell me.
possible. Over.
Yes, it's impossible with that. It's because, so one of the resources I've taught Calc 3 out of before used K as their usual term of integration, right? Their integrating piece. Not integrating piece, but their,
Variables.
the variable. And then another book I've used has used n, and so at different points I've switched back and forth, and that's why. At any rate, test, what would you use?
Would ratio test work?
It might. Ratio might work. We could try that. What else do you see as a possibility to try? The integral, I think, is a nice one on this
Integral
one.
would be the best, just because it's not gonna.
Yeah, if you happen to notice on this one with the integral, because this one's cubed and we have an n squared down here, integral test with u substitution would be a nice one on this one. Ratio might work as well. So that's fine. If you use integral, like I said, your u substitution would be, it'd be negative n cubed to go with on that. Yeah. Okay. Yes, go ahead.
Never mind. I was just asking if you brought us to the bottom, like you or.
Yeah, you could rewrite it that way if it's helpful to see. That wouldn't be a problem, for sure. Okay, so you have the homework listed. I believe when you look at this list of homework problems where it says 9 through 14, that one's the one that just says, like we just did in 5 through 8, where it says, which one do you think you might want to use? Okay, I believe that's true. And then the rest of them are the ones where you're actually practicing using the ratio and the root test.
Graphs, like it shows graphs and it says